Welcome to week number 4, in which we will study a fairly new concept, moments. Right? We'll cover the vector cross product, which is another operation with vectors. I don't want to spoil the surprise, but we will use a cross product to calculate moments. But what is a moment, right? What is a moment? So allow me a little bit of kind of a freestyle lecture here. I have here, I think it's a very nice figure, courtesy of the internet. And I have you may or may not have been in the position of this guy, right? Fixing an old piece of machinery with a gigantic wrench. But I think it's fairly clear what he's trying to do, right? He's trying to apply some rotation to that piece, right? Maybe it's a stock. Or something, right? It's broken, but he's applying a rotation. Right? He's applying force. To me, he seems like he's pulling the wrench in this direction, right, towards himself, and then he's applying torque, right? He's applying torque or rotation, right, or rotational force. Let's call it rotational force to that component, which may be stuck. Right, and then you may agree with me, right? I hope you agree with me that the sense of this arrow goes in that way, right? If we visualize the type of force he's using, the position of the wrench, let's agree that the rotation will have that sense. So indeed, he is applying a moment, right? This is an illustration of moment. So he is applying moment here. So what does he need to do to apply moment? He's applying a force here, right? So he's applying a force, right? And you would agree with me that this wrench, right? The longer the wrench, right? the longer the wrench, right, the higher the rotational force that he is able to apply. Right? So the rotational force is proportional to F, and it's also proportional to D, right? The distance or that length of the wrench. And that rotational force, right, is what we call moment. So moment is proportional to force and distance, right? Proportional to force and distance. So let's actually give a little bit less than a formal definition, right? But we will define in this topic moment is equal to force times distance, right? That is the definition of a moment. Not any force and not any distance. So let's take a look at how moments, which are rotational forces that cause rotation, right? That cause rotation. Let's see how they look in 2D. So I have here a Cartesian plane. Right? Let's just write here that it's 2D. And I have a force, right? I have a force here, which is perfectly vertical. And I'm going to identify a point in the origin called O, point O. So this is O for origin. So, but my point is here located at the origin, right? At 0, 0. And I have my force here. And I want to calculate the moment that this force makes with point O. Now, if we go by the definition, right, we may say, well, it's force times distance, so all I need to do is just to plot a distance here, and let's multiply times force times distance is equal to the moment, right? Now, the definition of this of moment requires that the distance is a special distance. So let me use the eraser here for a minute, and let's try again. So actually, right? Let's provide a definition and let's work a few examples, and then the hope is that it makes sense, right? The definition has to be consistent. If there is no definition, right? Somebody could say, well, you know what? I can define a distance here, and then another person could say, well, you know what? I'm going to define my distance over here. Another person may say, well, you know what? Forces have lines of action, so it's the same if I want, right? So I could even define a distance from a point in the line of action, and all these distances will be different. So we'll have three different moments caused by the same force on the same point, and that cannot be. So allow me to use the eraser here, and then I'll just keep my force over there, right? And then let's arrive to a consistent definition. So it just so happens, right? Let's just make a force over here. It just so happens that yes, forces have lines of action. It have lines of action. And the distance we are going to use in the formula, right? The distance we are going to use in the formula, right? This distance over here in the formula is if it has a very, very particular definition, right? So, right, equal to the force times the distance, right? But that distance is going to be the shortest distance, right? The shortest distance between the line of action of the force to the point I want to obtain the moment. I want to obtain the moment. Right? So that is a quite long definition of distance. So let's see if it makes sense, if we can actually have it nailed down in an easy way. So here is my line of action of F, and then according to the definition, this distance D is the shortest distance between the line of action and the point. So you would agree with me that this is the distance that we are looking for. Right? It's the one that makes a right angle, right? It's perpendicular to the line of action of F, right? So it's another definition of it. So this is the for the moment that this right, the moment caused by force F, by the red force is equal to F times D. Let's have another example. Let's have a blue force just floating in space. Let's what about we draw it over here, and we have to we want to calculate the moment caused by the blue force about my point O. Well, the first step is we have to project the line of action of my blue force, and then draw a perpendicular to that line of action that passes through point O. So this one, I think, right, it should be something like this. So perpendicular, and this is my V for the blue force. So M in the blue force, right, it's equal to F times D, right, all blue. What about another one? Let's have another force. Let's have a green force that goes, what about we draw it this way. So again, line of action, right, this is the green force, line of action, and then we have to find the perpendicular distance which that passes through point O. So what about this one over here? So this is my green distance. So the moment about O caused by the green force is equal to F times D, all green. Right? So that is the definition of moments. So we have been calculating moments, right? So take a look. We have obtained moments, and then we learned that that these distances refer to the line of action of the force D, and it has to be right, or it ends up being perpendicular to the line of action, right? So it's fairly straightforward in 2D, right? Let's go one step further and let's imagine we have the 3D plane. Yes, we will have to calculate moments in 3D space, right? You kind of knew that we were coming this way, right? To calculating moments in 3D space. So let's use what color do you want for the moment? What about red? I have a force floating in space, right? I have a force floating in space. Now, forces floating in space are quite right. They make us go crazy with the trigonometry involved, right? And we have a point O that lives in the origin, and of course, right, we can calculate moments about points that are not only at the origin but anywhere in the 3D plane. But at this point, let's just make it straightforward. Let's put our points in the origin, and we have to calculate the moment caused by the red force. So what is the moment at point O caused by that force? So it's the same concept. We have to find the line of action of my force floating in space, and this line of action is also floating in space, right? This is the line of action of F, and it's also floating in 3D space. And we have to follow the same principle, right? One of these points in the line of action, right? In one of these points, we can shoot a line. We can shoot a line to the origin, right? In one of those points, in this figure, I think that point is actually in the force F, or appears to be, right? One of these points make a perpendicular with the line of action, and it passes through point O, right? So this will be my distance. So in the same way that we define moments in 2D, right? The exact same definition applies for vectors in 3D. Now, right, in 3D, it's kind of tricky to find that shortest distance. And then, if you remember, you may or may have not have a course on analytical geometry, right, in 3D space. But I mean, if you have had all that course, you would have equations for the 3D vector or the line in space, and there are formulas, specialized formulas to find the shortest distance to a given point. But those formulas are quite complex, right? Quite complex. Imagine I give you an arbitrary vector, right? So what about this one over here, right? The orange vector F, right? Completely arbitrary, and I give you a point in space, right? Also floating in space. Let's make it orange just because, right? So this is the orange point. Let's call it A, and I ask you, okay, give me the moment that the orange vector is making about point A. Well, line of action, right? Line of action, same concept. Well, graphically it works, right? But when we get, right, and then this point appears to be here, right? So this orange line we want, which is perpendicular to the line of action, appears to be there. So now, right, imagine it's going to get really, really complex, really, really fast. And if we don't have any other tool, this is going to be a nightmare, a trigonometric nightmare, to try to find that point, right? To try to find this point over here, right? This is going to be, only with trigonometry, this is going to be very tricky, right? Very tricky. So some of you may be thinking, well, they are going to give us another tool, right? They have to give us another tool so we can actually are able to calculate moments in 3D space. Let me give you another one. So that's another vector, right? They have to give us a tool, right? They have to give us a tool that we can actually find the distance d in an easy way. They may give us maybe the coordinate of the tip of the vector, right? So x at the tip, y at the tip, and z at the tip, or maybe a point at the tail, right? So x at the tail, y at the tail, and then z at the tail, right? Maybe given these two coordinates, right, they have to give us a tool. They have to give us a tool to find that distance in a systematic way, right? Otherwise, it'll be tremendously difficult. Well, the good news, right? The good news is that yes, we are going to provide you with that tool, and it won't just be as easy as just okay, give me the coordinate, any coordinate in the vector, and then voila, you have the distance d, right? But it will be close, right? The tool that we are going to study is a very powerful tool, and the name of the tool is the cross product, right? It's a cross product. It's a cross product. When applied to a 3D vector, right, it doesn't matter which point of that vector you know, right? You will always be able to find the shortest distance. And you know what? It works for 3D, of course, and it works for 2D, right? And I'm sure it works in other dimensions. But yeah, so this is the name of the game. We will be studying cross product, and then we will use the cross product to calculate moments. Well, thank you very much. See you on the other side, in which we will define moment in a rigorous way, and we'll present first 2D examples, and then we'll extend that to 3D. Perfect. Well, thank you, and see you on the other side.